To understand commercial nuclear power, we have to throw out the common analogy of a glorified boiling tea kettle. A modern pressurized water reactor is a precision engine built on first principles quantum mechanics and extreme thermodynamics. Looking down into a reactor core grid, the massive physical scale and geometric complexity of the containment area become clear. Despite the size of this machinery, it is not designed to combust any physical material in a traditional chemical sense. Every single component in this facility exists for a single purpose: to safely harvest an invisible subatomic anomaly. The absolute governing law of this reactor is Einstein's E equals mc squared. The process begins when a lone neutron strikes a uranium-235 atom, briefly creating a highly unstable isotope called U-236. This unstable atom immediately and violently tears itself apart into smaller fission fragments, typically elements like barium and krypton, while releasing a few new neutrons. A precision digital balance scale compares our starting materials against the resulting fragments. If you weigh the resulting fragments and freed neutrons, their sum mass is slightly less than the original U-235 atom. That tiny missing weight is the mass defect. It converts directly into an immense wave of kinetic energy and heat. The fundamental operational goal of the reactor is simply to capture the intense heat generated by that vanishing mass. The neutrons released during this split are born moving at roughly 16,000 kilometers per second. But there is a mechanical problem. Surrounding uranium-235 atoms cannot easily catch or absorb neutrons moving at that blistering speed. The primary solution is the moderator, ordinary water. Fast-moving neutrons violently ricochet off stationary water molecules. With every collision, the neutron loses kinetic energy and momentum, slowing to a gentle drift of just 2.2 kilometers per second, reaching thermal equilibrium. Once a neutron is thermalized to the specific velocity, it is highly likely to trigger the next uranium split. Without water acting as a physical brake, the neutrons would pass right through the fuel, and the chain reaction would instantly starve and die out. When a uranium atom splits, 99.3% of the resulting neutrons are released in the exact microsecond of fission. If all neutrons were prompt, the reaction would multiply so quickly that no mechanical control rod could physically drop fast enough to contain it. The remaining 0.7% are delayed neutrons. They are emitted by the fission fragments seconds or even minutes after the initial split. This microscopic fraction of delayed neutrons acts as an essential time buffer. They slow the multiplication curve just enough for human operators and mechanical systems to safely throttle the reactor's power. Natural uranium, dug straight from the Earth, is nearly entirely U-238. It is useless for a commercial light water reactor. To make it viable, the raw material undergoes enrichment, a process that increases the concentration of the fissile U-235 isotope to 3 to 5%. This enriched material is then baked into small, hard ceramic cylinders of uranium dioxide. Just one of these pencil eraser-sized fuel pellets contains the energy equivalent of a literal ton of coal. Once inside the core, engineers face a physical containment problem. They must trap the highly radioactive fission byproducts, but they cannot block the flow of neutrons required to keep the reaction going. The specific metallurgical solution is a zirconium alloy known as zircaloy. Zircaloy is chosen for one defining trait. It has a very low cross-section for neutron absorption. Neutrons pass freely through the metal without being consumed. Hundreds of the ceramic fuel pellets are stacked end-to-end inside long, hollow zircaloy tubes. These individual tubes are then bundled together to create a massive fuel assembly. The final assembly operates as a material science paradox. It is perfectly designed to nurture a subatomic fire while flawlessly caging its deadly radioactive ash. With the physical fuel loaded into the core, the focus shifts to the human operators tasked with controlling the reaction over long durations. The core metric operators use to manage the reaction state is the multiplication factor, denoted as K. This animated diagram shows the neutron generation curve. When K is less than 1, the reactor is subcritical, and power drops. When K is greater than 1, it becomes supercritical, and power rises. When K equals exactly 1, the reactor is critical. The generation curve locks into a perfectly flat line, representing the steady-state target for normal operation. Maintaining this state over an 18-month fuel cycle presents a challenge. To run that long, a reactor must be loaded with too much fuel on day one, which immediately threatens a supercritical spike. Operators counter this using chemical shimming. By dissolving boric acid into the cooling water, they intentionally absorb the excess neutrons. As the fuel depletes over 18 months, the boron is systematically filtered out to match. They also mix burnable poisons, like gadolinium, directly into the fuel pellets. These materials absorb neutrons early on, naturally transmuting and fading away at the exact rate the uranium depletes. Maintaining a K of 1 is not a static dial setting. It requires a highly dynamic 18-month chemical choreography to balance a constantly decaying fuel source. Outside the fuel assemblies, the primary cooling loop circulates water to absorb the core's heat, reaching temperatures of 600 degrees Fahrenheit, or 315 degrees Celsius. This introduces a thermodynamic paradox. Water naturally boils at 212 degrees Fahrenheit. If steam bubbles were allowed to form inside the core, they would displace the liquid water, ruining the neutron moderation and stalling the reactor. To extract 600-degree heat without allowing the water to undergo a phase change, engineers raise the environment inside the primary loop to 150 times normal atmospheric pressure, roughly 2,250 psi. The specific component responsible for achieving this extreme pressure is the pressurizer. The pressurizer is a separate vertical tank connected to the loop. By intentionally boiling or condensing water inside this single tank, it acts as a massive hydraulic piston, crushing the entire primary loop under 2,250 psi to prevent boiling in the core. By mastering quantum mass defects, engineering perfect neutron moderation, and manipulating thermodynamics at crushing pressures, we successfully chain a subatomic event to the electrical grid.